principle of conservation of mechanical energy, it certainly becomes very handy when we are using when we are doing circular motion in a vertical plane. And we have done lectures on circular motion also, and we have done cases of when the body has been moving in a vertical circle. If you have done it, that is very fine. Otherwise you can go and after this lecture, once we are through with work per energy, you can go to the circular motion lecture also. That is, there you can understand few important concepts. Had we been using equation of kinematics, then we know that is all the time the tangential force is changing because this angle is already changing. So the component of mg this way is all the time it is changing. So you cannot use directly equation of kinematics, as we have done in the earlier case where it was along the inclined plane and it was axis was g sine theta, that is 5 meter per second square. It was constant. So you have very safely used equation of kinematics. But over here, the variable force, that is tangential force, is changing as this pendulum is coming over here. This is circular motion where there is a mass of 1 kg. This is 2 meter. Is the length of the string. It is tied over here so that it can oscillate in this circle, in this vertical circle. So over here we see that tangential force, the mg component, will always be changing because theta will always be changing. So acceleration will be variable acceleration. When the variable acceleration, you cannot directly use equation of kinematics. So over here, look, that is how easily, how comfortably we can use conservation of mechanical energy to find the velocity. Otherwise it would be very difficult to find velocity from here to here. That is, what is the velocity when it reaches over here, or when the velocity is when the body reaches over here. But using conservation of mechanical energy principle, it becomes very simple. Let's do it. Let's say it has been released from here, that is velocity is equal to 0. And we are supposed, let's say this is position A, this is position B. We are supposed to find what is VB, what is the velocity over here. So let's take it as this as reference level. We have taken this as reference level, and this body is moving in a vertical circle, semicircle. It cannot go beyond that. It has been just released from here. So it will come over here, it will go just retard, and over here just become equal to 0. And then once again, this will start its reverse journey. So over here we see that is there are no dissipative forces. This string is ideal, massless. There is no extensions. No energy is being consumed by this. There is no air resistance. There are no dissipative forces. So the sum total of kinetic energy and potential energy, that is mechanical energy of this system, is conserved. That is constant for all the situations, whether it is here, between we can use between any 2 points, and we'll see that is mechanical energy of this mass is going to be constant. So we have to find what is VB over here. So there are no dissipative forces. We can say mechanical energy A is equal to total mechanical energy at B. So potential energy at A plus same thing, kinetic energy A is equal to potential energy at B plus kinetic energy at B. This we have done in circular motion also, when we have done motion of vertical circle. So over here, this is 2 meter, this length of the string is going to remain same. So when we talk about the potential energy at this point, so obviously if this is 2 meter, so this is also 2 meter. So over here, potential energy at A is going to be mg. We have written as g because m will eventually get cancelled. So mg, h is 2 plus kinetic energy is half m, velocity is 0, is equal to potential B, that is mg 0, because this is the reference level we have taken. This is our reference level. What is the height of this particle from this reference level? Body is a point mass. So it is 0 plus half m Vb square. So this is 0, this is 0. So it is mg2 is equal to half m Vb square, m and m they get cancelled. So it is 2 or 2, 4 into g, that is 40. So root 40 is equal to Vb. We have easily got what is velocity at this position. Similarly, we can find the velocity at any other position in this vertical circle.